Okay, hello everyone. This is a love story. I'm Jeremy Hughes. I'm from New Zealand, and everything I'm going to describe I saw with my own eyes. These are the four colourful characters that will dominate the story: Scala, JavaScript, DTS, and TypeScript. Don't be put off by their appearance. Some are friendly, some are dangerous. The worst are both friendly and dangerous. This is Scala. Classy, expensive tastes, Platonist. Likes Bertrand Russell and European history. Complicated but in an endearing fashion. This is TypeScript. A pragmatic empiricist. Likes the outdoors, admires Wittgenstein. Here are some of the features of TypeScript. I'm going to go through them one by one with some code examples. TypeScript is structurally subtyped. So in this example, Y is a subtype of X. For structural reasons, not for nominal reasons. So Y can be assigned to something that has the type of X. Has untagged unions, just like Scala 3. Has intersections. So in this case, we have a type X and a type Y. The type Z has properties of both X and Y. So it has alpha of number and beta of string. Has a thing called index type accessors. So you have an object, in this case A, and we can ask what is the type of the property on A of this literal string type. So here is the function value at, just saying give me a key that exists on type A, give me an object of type A, and I'll give you the value correctly typed at that location on A. So say we have an object containing the name and the height of the world's tallest man, and we want to get height, we can pass in height and get back a value which will be correctly typed as number. If we passed in something other than height or name, that would cause a compile time error. TypeScript has conditional types, which are similar to Scala 3's match types. Example here is, say I have a codec, which is a way of getting from a type A to some sort of binary or other serialization type O and back again. I might want a convenience of a method to JSON on this codec, which is only applicable to a codec where type O is a subtype of JSON. So here I can use conditional types, which here I'm saying if O is a subtype of JSON, then I require a value of A, and I'm going to return its encoding in JSON. Otherwise, you can't give me anything. It's a never. So if you try to call this method on a codec where O does not extend JSON, it's going to be a compile time fail because you cannot give a single value to JSON that will be correct. Perhaps a more familiar example is something similar to what Martin gave in his keynote, where we have a tuple type. So here it's a union of empty and pair. TypeScript only has untagged unions, so we emulate tagged unions by having a literal type tag there that's either empty or pair, and that's what allows us to discriminate between the two. And then we have this concat type, which uses the conditional typing of TypeScript to say if X is a pair and Y is also a pair, then we're going to return a quad Otherwise, you'll just get X's or Y's. I've got a demo that shows this working, but I can show you at the end of the talk, not during, because it's such a hassle to switch between. It also has map types, which is a way of encoding something similar to higher kinded data types in Scala, where you have a data type that takes maybe a functor, so that the values could be identity or option or that kind of thing. So here we pass into a map type this type literal of alpha of number and beta of string, and the map type says for every key in whatever type you pass me, pass back an array. Pass back for that key a value which is an array of whatever type is at that key. So pass in alpha of number, beta of string, and get back alpha of array of number and beta of array of string. This is JavaScript. JavaScript is a typological nihilist. Everyone's friend. Everyone's unpredictable wackadoodle friend. You never knew just by looking what the yellow clown would do next. The bravest or most foolish among us didn't let this bother us. However, cautious acquaintances wished they could invite the clown over to cook dinner before inviting the clown over to cook dinner, just to make sure that cooking dinner didn't also include setting fire to the house. Finally, this is DTS. And DTS's favorite trick is to dress JavaScript up in TypeScript's clothes. This fools most people most of the time. When you compile a TypeScript file, what you get out the other end is a file of JavaScript and a file of TypeScript type declarations, which is a .dts file, .d.ts. And those files are then consumed in turn by TypeScript again if you depend on that module. If you're pulling down a module that's just purely JavaScript, you can provide a manually written .d.ts file describing the types of that JavaScript module. That's what DTS does. Those are the characters in the story. So here goes. Once upon a time in a far-off land, the land of New Zealand, there was a hill, and on that hill Scala and TypeScript met one sunny day. The attraction between them was palpable, so Scala ventured a friendly greeting. TypeScript clearly did not understand. The attraction was mutual, so TypeScript said hello. Scala did not understand. So when your first attempt to get them to understand each other is to plug the code from one into the interpreter of the other, this is what you get. It kind of doesn't work. What a bad start to what could have been an epic romance, thought Scala. Scala went home depressed. Why bother? And even if there is a reason to bother, how are we ever going to understand each other? And even if that works out, when will we elope to the land of general availability on GitHub? It's going to be the structure of the story. Why, how, and when. Why? Why have this relationship in the first place? Well, once upon a time there was a project. The project had a client which had to use JavaScript, yet be protected from JavaScript's unpredictable nature. Had a server, written in Scala, of course, and a kind of no man's land in between. Code that needed to be flexible, to be run on the server or the client where necessary, largely because we didn't yet know what we were doing. And this is a project where there was a budget for experimentation that contained just enough latitude to reach into the unknown and find love. What we needed to do is run on both the server and the client, but expose something better than untyped JavaScript to the client. Yeah, nah. Love doesn't need a reason. How did this come about? Well, Scala got up early and climbed a tall hill to get a better sense of perspective. Scala's friends came too. Everything looks so simple from here. It's like standing on the shoulders of giants. If you don't know, this is the logo for ScalaJS. So thanks ScalaJS and everyone that built it. While up there, the four friends had an epiphany. Scala and JavaScript could communicate. JavaScript and TypeScript could communicate. Therefore, by transitivity, Scala and TypeScript could communicate. DTS in particular was delighted. ScalaJS gets us JavaScript already. All we need to do is supply TypeScript type declarations for the JavaScript output of ScalaJS, and boom, we're done. Creating the type declarations is all we need to do. So the friends tried it out at once. First, Scala stood and improvised a short poem about length of string. Then JavaScript rendered an interpretation. DTS saw that JavaScript had left out some important information, so DTS added it back in. So for obvious reasons, JavaScript left off the types and DTS put the types back. TypeScript heard and understood, so everyone was very happy. The end. It's a really kind of concise example of what you get. Put in ScalaJS, get out JavaScript, write a declaration file for the JavaScript, and then you can consume that from TypeScript. Not the end. There are two problems. Problem one is that DTS's second favorite trick is misrepresentation. And here's an example of that. DTS provides a file containing a declaration for the current time, get now. TypeScript consumes this and creates a function for getting the current epoch, number of milliseconds since Unix 0. Everything type checks and blows up at runtime because get UTC milliseconds is not a function on date. Why is this? Well, it's because DTS lied. What JavaScript actually said was that get now returns a string. So this is something that DTS is very fond of. Misrepresentation. Here's another example. Scala and TypeScript. Scala wants a flower, presumably as a sign of affection. I would like a flower. TypeScript, of course, I'll give you a flower. Here's a flower. However, unbeknown to Scala and TypeScript, TypeScript has once again been tricked by DTS. So DTS is green, and it's presumably told TypeScript that, yeah, here's how to give a flower. But at runtime, what's happening is it's giving a flame instead of a flower. So Scala dies in flaming agony. Problem is that TypeScript trusts DTS completely. So if you make a change to whatever generates JavaScript and forget to update your definition files, you get runtime problems. If something you're depending on, some upstream library makes a change and you update and don't realize, and you don't change your DTS files, then you're going to get problems at runtime. If you update your DTS files but make a typo that type checks, then you're going to get problems at runtime. It's the worst of both worlds. You have the confidence of types and the runtime failures of no types. So if you use DTS in this vanilla way, you will be sorry. The second problem is that, as we alluded to before, Scala is a Platonist and TypeScript is a pragmatic empiricist. So Scala believes in the Platonic abstract ideal of duckness, for instance. TypeScript believes that if it looks like a duck, it is a duck. So Scala says, here's a duck, and here's how you give me a duck. TypeScript goes, all right, I've got a duck, and I'm going to give you a duck. Little type checks, it's sweet. And Scala blows up at runtime. Well, the JavaScript runtime blows up. Because you gave me an object which happens to have a name, and I really wanted a duck. So this is because Scala is nominally subtyped and TypeScript is structurally subtyped. Those are the two problems we need to overcome. DTS lies and produces definitions that are just plain wrong. And secondly, Scala requires nominal types from TypeScript, which doesn't believe in them. So we could say, in terms of the story, once upon a time there were four friends. JavaScript, who could speak but was unintelligible. DTS, who could interpret but was a pathological liar. TypeScript, who trusted DTS implicitly, and Scala, who was pedantic about abstract Platonic ideals. How do we progress the plot? Because we want these guys to get together. We need to put two constraints on DTS. Constraint number one is we generate our DTS from Scala. So we cut out the manual process. So provided our generation is correct, we're not going to have the update problem. DTS won't be just wrong or lying its face off anymore because it's being generated from the source of the types to begin with. Constraint number two is that we emulate nominal types in our DTS definitions. Here's an example. Here's a duck. Here's how to give me a duck. And if in our DTS file, say, well, here's a duck and it has a name of type string, but it also has an additional property with a unique name, fully qualified name of duck. It's the easiest way to get a unique name, of type never. So it exists only at the type level. But it makes duck structurally unique. So then, if TypeScript says, well, here's something that looks like a duck, gets a type error instead of a runtime error. Because what you've given to gimme is missing this, this property, fully qualified name of duck. That's how we can emulate nominal types in TypeScript. So those are the two constraints. One is the process of generation, and the second is how we create nominal types. And now they lived happily ever after, for real, the end. What I've got now is some examples of translating from the Scala types into the TypeScript definitions. Here's a Scala trait which has two members, alpha and beta. Pretty straightforward translation into a TypeScript interface with the addition of this, this property that only exists at the type level. Same thing with classes, really. We have an interface which describes the class just the same as the trait, and an interface which describes the class constructor, which in this case takes an alpha of string, and then we declare that there's this value, a class, which has the type of the constructor, and so now we can construct values of this class by supplying a string. It'd be tempting to leave off that second definition in the class constructor, which contains the new, because as we've all heard, new is passé. We don't do that anymore. But that new definition is how the TypeScript compiler knows that something can be an instance of a class, so it's necessary. We need to keep it around. Objects are just interfaces that have a value implementation, and the value side of all this stuff is supplied by ScalaJS. So we're just supplying quite literally just the types. So here's how in TypeScript you'd get at this default value. We can create unions. So for a Scala type that's kind of like either got result, which can either be a success of A or a failure of B. In TypeScript, we generate two interfaces that share a common base. So success and failure, success of A, failure of B, never instead of nothing does the same thing. And then highlighted in pink is what turns it into a union. It's an untagged union, but because it's a union of two classes, we can use instance objects to fold over the different possibilities. And TypeScript is flow typed, so if res is instance of success, then the res that gets passed into do success has a type of success. And same for do failure, and by the time you get down to total, res will have a type of never. And so what the total function does is provides a compile time check that this fold is indeed total. And if something weird happens at runtime, it's going to blow up with the inconceivable message. What we could do to get slightly different ergonomics is add a tag to each of the classes. In this case, a property called $variant, using shapeless to create literal types of string, success and failure. Under Scala 3, obviously, we won't need shapeless to do that. And then what gets generated is pretty much the same as the previous slide with the addition of these variant fields and a mapped type called iResult, because we end up indexing on the type of variant. So success maps to the type of success and failure maps to the type of failure. And then with a little bit of extra one-time only type definitions, we can create a function that will fold over any union that's been generated using this mechanism. So first of all, we define a tagged union as any union of U where the objects of the union contain this variant property. And then what we end up passing into the fold method is this object union fold cases, which is a map type that says for every case in the union, we need a function from that case to whatever the result of the fold is. The advantage of this over the instance of approach is that we get a label for each of the cases in our fold. When you've got many cases, it's handy to have labels so you know where you are. So we've got the success label and failure label for each of the cases in the fold. A third possibility, which is one I'm finding increasingly, well, I guess better because there's less boilerplate, and yeah, is to create the fold cases type in Scala instead. It needs to be inherit js.object so that JavaScript semantics apply, including the ability to pass in a structurally conforming object rather than one that has to be nominally typed. And what that means is that we can call fold without having to supply the extra TypeScript stuff that we did in the previous slide. So we get the same ergonomics without the extra types being necessary. TypeScript doesn't do higher-kinded types. There's an encoding, a lightweight encoding similar to what Elm uses, but it's pretty awful. So if we have an abstraction on the Scala side which takes a higher-kinded type and we want to use it on the TypeScript side, we need to kind of fill in the hole. So if we have a type alias, then that gets turned into a filled-in interface on the TypeScript side. So in this case, abstraction of array, we get an instance that's populated with array as f. Final things are largely going to be obsoleted by Scala 3. Using the Statico Scala new type package, we can create new types on the Scala side, and they generate a tagged type on the TypeScript side. So here there's a fully qualified string literal type, which is used as a key, as a tag, and in this case, well, on the Scala side, we're creating a new type of string. So on the TypeScript side, we have a string intersected with a type tag of the type of key. The intersection is something that exists only at the type level. So at runtime, we've got a string, but at type check time, we have a string intersected with this unique tag. That means that the only way to create a value of that type is with this tag method, unless you're being deliberately nefarious and you cast to the tag type. To create a refinement, instead of supplying something that simply tags, you want to supply something that checks and tags. Ideally, you'd return an either. There wasn't enough room on the slide, so I'm just going to throw. If you want to make it opaque, you switch new subtype for new type on the Scala side, and string for void on the TypeScript side. Void has no methods on it, so the only thing you can do with the value of this void intersected with the tag is whatever methods you've supplied on the Scala side. In this case, the only method is make or throw, so we're kind of out of luck, but we could have added something else on, like concatenate. You can do unions of literals. It's pretty awful. I'm pretty eager to see it go away, and I think Scala 3 will make that possible. At the moment, it's kind of there because we need to use it internally. As you can see, it relies on some annotations, which is kind of yuck. One problem we kept coming across was needing to pass types like either across from Scala to TypeScript, and because ScalaJS only emits JavaScript methods and things for types that have been annotated, you don't get it for something like either. So it's tempting, and we tried initially to implement something like either on the ScalaJS side so that we could use it in Scala and also in TypeScript, but eventually came to the realization that it seems to work better if we implement either in TypeScript, because we get TypeScript semantics, TypeScript syntax. It just seems to work better with the rest of the app. And instead, from ScalaJS to just export this really simple either like object, which just contains the fold method. And then at the use site in TypeScript, you can just wrap it with the either type we've implemented in TypeScript. So what we've got automatically generated from the Scala types are traits, classes, objects, unions, and new types with a few caveats. Everything's read-only. So if you want to mutate something, you need to create a method that takes the new value and do that in Scala. Everything's unconstrained. There are no generic type constraints yet. I don't think they'd be too difficult to implement, at least simple ones, but hasn't been necessary. And there's no variance. Because TypeScript is structurally subtyped, it kind of does the variance thing without needing annotations, but we haven't really explored how that would work between ScalaJS and TypeScript. When would you want to use this? If you can do everything in ScalaJS, then do that. If you don't need to consume ScalaJS from JavaScript, then by all means don't. That's probably the best thing. But if you need to consume ScalaJS from TypeScript, need to consume ScalaJS from JavaScript, then that's where this comes in really useful because you get types. If you want to consume JavaScript from ScalaJS, then you're going to have to use something else. And here are some possibilities. For the Scala to TypeScript direction, there's an existing project, Scala TSI, which takes quite a different approach. It's worth checking out. And for the opposite direction, there's Sebastian's ScalaJS TS importer and this other project as well. When's it going to be available? The answer is I don't know. This is kind of part experience report as well as going through how we did it. The current implementation is a proof of concept as an SBT plugin. In the future, I think it would be worthwhile investigating integrating something like this into ScalaJS. So as a flag or as a default, you would just get types as well as JavaScript out the end. And at some stage, I'm looking forward to seeing how the changes that have come with Scala 3 are going to influence what we do, particularly literal types and untagged unions. That's it. Question time.
So you just mentioned towards the end that you would see something like that integrated inside ScalaJS. What benefit do you foresee from that integration versus an external tool that can evolve in more freely?
Expertise, access to expertise perhaps. At the moment, what we've got is a result of me largely kind of figuring out how Scala's type introspection stuff works on the fly, so it's pretty ugly. I guess initially I'd like to look at the internals of ScalaJS and see how that works because it'll probably help my implementation. But also the possibility of having everything kind of generated in one pass without having to match things up.
Yeah, I have bad news for that. Because, I mean, sort of for your first expectation, ScalaJS works on the erased types anyway. So
right.
Everything like type parameters you wouldn't get in any reasonable way. And so that feeds into your second expectation, which is you could do it in one pass. Well, not really.
Right. Okay.
You would have to do it in two passes anyway. So, yeah.
So then Tasty is probably a more interesting future prospect.
Tasty is Tasty solves problems, but nothing related to ScalaJS.
Right. Okay.
So really, the compiler plugin or the Scala meta-based. So the compiler plugin would be your one-pass thing because you would inject a face somewhere in the beginning of the compiler.
Right.
But otherwise, like none of the other things is going to really help you there.
Right. Okay. So stick with an external library that we can use through SBT or a compiler plugin.
Yep.
Good to know.
Yeah.
So if I'm a TypeScript programmer and Scala gives me a duck, can I actually use the field that's used as a tag and that has type never?
No.
Which would be a lie, right?
No, it's not. Well, you could certainly try, but the reason that I had it as a string keyed field starting with the @ symbol is kind of like it's not going to just automatically autocomplete for you. Stay away, don't use this. Yeah,
right.
It's a fairly common idiom.
Fair enough.
Yeah.
But maybe you could do something that even if used doesn't lead to unsoundness, right? Like make up a type that's not usable.
Yeah, you could probably make it private. And then you're not going to be able to use it or cast to it unless you really, really try. Yeah.
Anyone? Well, thank you very much. Sorry. Yeah. No.
I guess I have another question. So, I mean, by default, the classes that you write in ScalaJS are not even visible to JavaScript to begin with. So I guess those annotations that you generate are tied to JS exported members or things like that? Or
yes.
Or
yes.
do you do something else?
Yeah, no, it's tied to the ScalaJS annotations, which I neglected to include.
No, okay, that makes sense. Yeah. Thanks.
Yeah, we have some macro annotations to generate some of the ScalaJS annotations, but that's kind of irrelevant.
Yeah, it's all done. No questions anymore. Great.
Thanks.